So if G star x happens to be G prime star x, which it could be, there could be two different ways of getting to that element of the orbit, then the output should be the same. In other words, it shouldn't matter which choice of representative G or G prime I use. So I've got to check that first, otherwise I don't even have a function. Well, let's just do that. Suppose G and G prime both take x to the same place. I just want to unwrap this a little bit. In fact, I'm going to act on both sides with G inverse. So both sides are elements of big X, so I can apply G inverse to both sides using the action star. Okay? In fact, these implications are actually all going to be if and only ifs. And I will need the opposite direction a little bit later on, but I'll just keep the implications going in one direction just to keep it a bit simpler. Right, we're now going to use the fact that star is an action, so when I do something star something star something, I can put the two group elements together. So that's using the second property of star being an action. So that's using the fact that star is an action of big G on big X. And the things in brackets, the two objects in brackets are just group elements in big G. The one on the left, G inverse G, of course, is the identity in big G. And I can't do anything with the one on the right at the moment. So that's using the fact that G inverse G is the identity element. So that's just purely a computation in big G once we get inside this bracket. And then using the first property of star being an action, the identity element star x is just x. So that's using the first property of star being an action, that E star x is equal to x. And the right hand side is just waiting patiently for something to happen. That's not changed. Well, what does this say? Well, we probably want to read it from right to left rather than from left to right. It says that this group element fixes x. So G inverse G prime must be in the isotropy subgroup, because it fixes x. Okay, and by definition, anything that fixes x is in the isotropy subgroup. So G inverse G prime fixes x, it's in the isotropy subgroup, but that's precisely the statement that G and G prime are related via the equivalence relation that gives rise to the coset partition. So they must live in the same cell in the partition. So that's a slightly bigger step, because we have to go back to what it means to be in the same cell in the coset partition. So let me just say that again. G inverse G prime being in the subgroup is precisely the same thing as saying that G and G prime are related by the relation to which the subgroup gives rise. And if they're related in the equivalence relation, they live in the same equivalence class. In other words, they live in the same cell, so their cosets must be the same. So there's a bit of a jump there that involves previous stuff we've done. If you want to look back to when we did cosets right at the beginning. So the fact that they're related means they live in the same coset, so their cosets are the same. So we end up with ggx equals g prime gx, which in fact is what we're trying to prove. So that does require a little bit of thought. So hence, we do have a function. I mean, I shouldn't really have written it down until I checked that. From the orbit to the set of cosets, which takes g star x to g sub x. And I've just checked that this makes sense. It doesn't matter which g we use, we'll get the same coset. And now it's a case of checking that this function psi is a bijection. So we now check that this function is actually a nice function in the sense that it's a bijection. And I think the easiest thing here is just to check separately that it's injective and surjective. So let me just write down psi again. So that's our function. I mean, it's quite sophisticated, this in a way, because we're mapping from the orbit into the set of cosets. So this is a set of subsets. So this is quite a sophisticated function. So injectivity is where we need the reverse implications of the argument that I did a few minutes ago. I'll probably write it out in full. So how do we prove a function is injective? We take two elements of the orbit, so now these in principle could be different elements, and we'll assume that they go to the same place, and I want to prove that then that they're equal. Suppose two elements of the orbit get mapped to the same place. So psi of the first element of the orbit equals psi of the second element of the orbit. And I want to show that necessarily these two elements of the orbit are equal, because that will say that the function is injective. Well, if psi of g star x equals psi of g prime star x, that means that the two cosets are equal. And now I'm going to reverse the argument I had a few seconds ago. So I could have done it all in one actually, but it's perhaps best to spread it out. So that means that g inverse g prime is in gx, because if two elements, if g and g prime have the same coset, they live in the same cell, so they must be related by the equivalence relation, and the equivalence relation is that g inverse g prime is in the subgroup, so that's why that implication follows. And then I just, as I said, reverse the argument I had a minute ago. If g inverse g prime is in gx, it must mean that g inverse g prime fixes x. And I'm not going to write all the steps, but it's the reverse of what we've just done. We end up with g star x equals g prime star x. So there's a couple of steps that I haven't written down, but they're identical to the ones on the page a couple of minutes ago. They're just these lines here, but with these implications the other way. Okay? So these implications are going from left to right. For injectivity, you need them going from right to left, which they do. These are all reversible steps, but you need to check that. Okay, so we end up with, if two elements of the orbit go to the same place, they must be equal, so hence psi is injective. So that was another example of proving something's injective. Of course, every example is different in detail, but the basic template is the same. You start with two elements of the domain, you suppose they go to the same place, you end up showing they're equal. That's how you prove that something's injective. And then surjectivity, which is a bit easier. How do we prove something surjective? Well, remind you what the function looks like. We're going from G star x to G over G sub x. So to prove surjectivity, we take an element in the codomain. So we take a left coset, and we want to find something in the orbit that goes to that coset. Okay? So we take a left coset. So a left coset looks like that. It's an element times a subgroup. Well, which element are we going to pick in the orbit? Well, the one that involves little g. So given the left coset, we have a little g floating around here, and we use that to construct an element in the orbit. And then, by construction, what happens if I apply psi to this element in the orbit? Well, of course, we get exactly what we want. So each element in the codomain, each left coset, does come from some element in the orbit using psi. So that is, surjectivity was easier than injectivity. So I'm going through this fairly quickly. It's not a proof I would ask you to reproduce in the May exam or something, but you should be able to follow the proof. And you will be using this theorem next semester, so having seen the proof, at least you can rest assured that you've seen the result proved. So we conclude that psi is a bijection because we proved it's injective and surjective, and hence there is a one-to-one correspondence between the orbit and the set of left cosets. Okay, so that's the end of the proof. So it's not particularly difficult, but it does bring together quite a few ideas. The most subtle part is the stuff where we're talking about the partition and the cosets and the equivalence relation. That did come in at one point. So that did rely on our knowledge of the relationship between equivalence relations and partitions, which we've been talking about on and off all semester. So let's have a corollary to this. Suppose G is a finite group. So what I've just done applies to any group whatsoever, but suppose G is a finite group with the other hypotheses being the same, then for each x in big X, we have the size of the orbit times the size of the isotropy subgroup is equal to the order of the group. So I'm assuming that G is finite now, so this is an equation about multiplying two natural numbers together to get another natural number. This wouldn't make sense if G were infinite. So this is really this kind of seesaw effect that I was talking about earlier. The bigger the isotropy subgroup, the smaller the orbit, and conversely, because the product has to be the order of G. So if the isotropy subgroup is big, then the orbit must be small, and conversely. Okay? And the proof of this corollary is easy now. We know that the size of the orbit is the size of the set of left cosets, because these are in one-to-one correspondence. Okay, so these two sets we've just shown are in one-to-one correspondence. So if they're finite, they've got the same number of elements. I mean, even if they're infinite, their cardinalities are equal. So this follows from G star X being in one-to-one correspondence with G slash GX. But we know that the number of left cosets, I mean, that's sometimes called the index of GX in G. The number of left cosets, think of our bar of chocolate picture, is the order of G divided by the order of the subgroup, because that partition into left cosets is a regular partition. Each coset has the same number of elements. So hence the result. So just multiplying both sides by the order of GX, we get the result. So this is sometimes called the finite version of the isotropy orbit theorem. But so this is a precise statement that says if the orbit size is big, then the isotropy group must be small, and conversely, because the product has to be the order of the group. So that was the theorem and the proof. That'll be our last proof probably of the semester. Are there any questions or comments about that? I mean, I've gone through it quite quickly. It was part of your reading in Fraley, but you know, it's not a trivial proof. It does involve a few ingredients being brought together. And although you won't need to be able to reproduce the proof, you will be using this theorem next semester to prove the counting result. Are there any questions about that? So hopefully along the way we've practiced the idea of orbit, stabilizer and so on. So just before the break, let's do another example, and it's a kind of bigger version of an example that we did last time. And this is going to be an example that illustrates the theorem I've just proved. So let's think about a square. Now, this is a square that's supposed to be sitting inside the plane, and we know the symmetry group of the square is the dihedral group D4. So the group D4 acts on the square. Okay, it's the symmetry group of the square. It's the group of all distance preserving symmetries of the square. Now, as I said last week, once you've got one group action, you get a lot of other group actions for free. And given that D4 acts on the square, it also acts, for instance, on the set of 16 little squares that I get if I divide the square up into 16 equal little squares. So D4 acts on, well, 1 up to 16 once I've numbered these squares in some way, and it doesn't matter how I number them, so I'll number them like this. I'll go around in a kind of spiral. So it doesn't matter how you number the squares, I've chosen to number them like that. But remember, D4 consists of rotations and reflections. Rotations about the centre of the square, and reflections in the lines that bisect the sides and the two diagonals, and we've got notation for the 8 elements in D4. And notice that each rotation and each reflection moves one of these little squares into another little square. So for instance, if I rotate through a right angle counterclockwise, little square 6 goes to little square 9. Yeah? If I rotate through pi by 2 clockwise, or if I reflect in the diagonal that goes from southwest to northeast, little square 1 gets mapped to itself. The points in the elements of little square 1 get moved around, but the square as a whole, as a subset of the big square, gets left fixed in reflection in the diagonal going from southwest to northeast. So each element of D4 moves one of these numbers to another number by virtue of the little squares moving to another little square. Is everybody happy with that statement? So another way of saying this, we actually have a homomorphism from D4 to the symmetric group of this set, and of course we'd usually call this S16, which is quite a big group. Got 16 factorial elements. So we can think in terms of the action, or we can think in terms of the homomorphism. And we could actually write down the image of each of the 8 elements of D4 as a permutation in S sub 16. We could use cycle notation, and we did a similar thing last week, I think, when we had 9 small squares. But what I want to do now is illustrate the orbit isotropy theorem. So we need to fix an x. Remember, we always wanted an x in big X in order to get that whole thing going. So let's fix 1 for sake of argument to start with. So I'm going to be interested in x equals 1. I'm going to compute the isotropy subgroup, and I'm going to compute the orbit, and then we'll see how the orbit isotropy theorem links the two. So we need to keep that picture in mind. Can I fit it down here? Perhaps I can. So I'm just going to look at the isotropy subgroup G sub 1. Now, which elements of D8 fix the square 1? Well, the first thing you write down always is the identity element, and the identity element in D4, in Fraley's notation, is rho sub 0. So that's a rotation through 0 right angles, if you like. So the identity element always is in us because this is a subgroup. The identity element fixes everything. Does any other element of D4, so there are another 7 elements of D4, do any other elements fix the square 1? Well, I mentioned one of them a minute ago. Reflection in this diagonal fixes 1. And reflection in that diagonal is actually, Fraley calls this the second diagonal, so reflection in there is delta 2. In fact. So this is the second diagonal, this is the first diagonal, this is the second diagonal, and reflection in this diagonal is called delta 2. So that reflection fixes that square. It moves the points of the square around within the little square, but as a whole, that square is fixed by delta 2. Does any other element, I mean there are 6 elements left, does any other element of D4 fix the square? So we've got the non-trivial rotations through right angle, 2 right angles and 3 right angles, and then we've got reflection in the vertical, the